Sorry.
The natural metrics we consider in a singularity that it's defining. So we consider germs of singularities that can be seated in Cn, and then the natural metrics are the outer metric that is given by the restriction of the Euclidean metric, and the inner metric that is the natural extension of the Riemannian metric given by the infimum of the lengths of the rectifiable paths joining two points. Okay, these are two natural metrics that are even defined, well defined, up to Bilipschitz mappings, and they do not depend in particular on the analytic embedding of the germ of singularities. Okay. Well, I recall what is the Bilipschitz mapping between two sets. There must exist a constant, positive constant, such that the distance between 2 points in the image is bounded by, okay, by this. Okay. Of course, this is not a new subject, but there has been a lot of development. Maybe after an inflection point might be set in the discovery by Maria Pe Pereira and Fernandez in 2008 of a complex singularity that is not a straight cone for the inner metric. For the case of complex plane cars, we know that, for example, with the inner metric, any car germ is Bilipschitz to a straight cone, and for the outer metric, a car germ with the outer metric is an equivalent data to the embedded topology. Okay. And what about for normal surface singularities? Pues the inner metric is known, the Bilipschitz classification of complex normal surfaces with the inner metric, thanks to Wirth, Neumann, and Pichon. And what is known is a thick film decomposition, okay, of the germ in pieces, in a piece that is a straight cone and some other pieces that are a kind of mapping cylinders of the cones and some interpolating annuli. So the inner geometry is completely known. And for example, for the outer metric is completely unknown, and there are some other related problems. For example, trying to classify for which surfaces the inner metric and the outer metrics are the same up to Bilipschitz transformation. Okay. Well, there has been a lot of activity recently. Well, for example, putting in relation the Zariski singularity and the triviality of the abstract Bilipschitz type for the external metric in a family of surfaces, or the relation between the abstract Bilipschitz type for the external metric and the multiplicity of surfaces. The question that guides us is to find a metric algebraic topology that codifies part of the Bilipschitz type. There were two previous theories by William Brasselet and another one by Valette that were closer maybe to intersection homology than ours. That follows closer the Poincaré approach. So our results are into papers. The first one, that is the homology theory that we call moderately discontinuous homology. That it's a work with Javier, André, Bobadilla, Sonia Gente, and Edson Sampaio. That is already accepted. And the second one is the homotopy part. That is where there is, in particular, a Hurewicz homomorphism relating the two theories. That is a work with Javier, André, Bobadilla, Sonia Gente. These works are partially included in the thesis of Sonia, and there is a third work in progress with Javier, Fernando Bobadilla, about the fixed D-point theorem, and he will talk about it later. Yeah. So let's see the setting of the theory. It applies to subanalytic germs. Okay, with a subanalytic. So it is a more general context than simply complex singularity germs. That is what I started to talk about. It applies to subanalytic germs with a subanalytic metric that might be more general than the outer or the inner, but this will be the main examples, the interesting ones for the moment. Well, these germs, subanalytic germs, have a conical structure, and then our theory would capture the different collapsing speeds of the link topology when we approach the origin. The theory also applies in a more general setting when we have a one-parameter subanalytic family with the outer metric, and in this case, the family is a germ in the space of parameters, and it captures, our theory would capture the different speeds in the degeneration of the family towards t equals 0. Okay. Since we want to measure this degeneration with respect to the parameter of the conical structure, we will always work with subanalytic maps, okay, always subanalytic because we want to remain in the category, that keep linearly the distance to the origin. That means that okay, this is a germ in 0 and this is a germ in 0. So the image of X has modulus between K times the modulus of X and 1 over K times the modulus of X for certain K greater than 1, and this constant doesn't depend on X, of course. So geometrically, the function does not have to change too much the distance to the origin, so it will transform the level epsilon to something between these two, these two areas, no? The sphere at distance k times epsilon and the sphere at distance epsilon over k. Okay, and in particular, our invariance is, the groups we are constructing will be invariant by subanalytic Bilipschitz mappings that have this extra property. In particular, they will be invariants, Bilipschitz subanalytic invariants for the outer and the inner metric. Because for these metrics, we have this condition for free whenever we have a Bilipschitz map. Okay. Okay, so I will make an abuse of language during the talk, but I already didn't do it. So whenever I have two subanalytic germs of some RN, I will simply write X and Y. So they will be always germs at 0. Maps will be always, would take the origin to the origin. They will be subanalytic, continuous, and they respect linearly the distance to the origin as before, in order not to destroy the information we are interested in. Important examples will be cones. What is a cone? So you have Rn, you take L, okay, and you consider the, okay. I will denote it like this. This is what I want to say. And another important example are the beacons. The beacons are similar, but here we have, we take t power b times x. Okay. So an important definition is the definition of B points. So we start with a germ, with a metric, T. Everything is subanalytic, as I said. So a point is simply an arc. That is a mapping from the segment that is in fact the cone over the point. That's why we call it a point, to the singularity. And now, for every collapsing speed B, we say 2 points, P and Q are the equivalent if if we think of t as the distance to the origin, if the distance when we approach to the origin goes to 0 quicker than t to the b. Okay, if we think of this depends on the metric, but if we think on with the outer metric, that is the easiest one maybe, then 2 points are the equivalent since they are given by has development of power series with rational coefficients, because they are subanalytic, then they are the equivalent if and only if they coincide up to order t, that is the order in t of the difference is greater than b, that is they are tangent of order b. Okay, it has a clear geometrical meaning, and in particular our theory was, I call B points will be a equivalent class of points with respect to this equivalence relation, and our theory philosophically identifies B points. Okay, identifies points with respect to this this equivalence relation, so it's a kind of algebraic topology for the set of B points. Okay, here I have an example. I have this surface that is almost a linear cone, but for example, these two curves, the blue one and the green one, are tangent, let's say of order 5. Then, as I said, for parameter, for example, then b equals 5, these 2 points are identified, and then study this surface will be the same as study this one. Okay, for the parameter b. With respect to the parameter b, they are the same. So our theory, given a germ with a metric and given an abelian group and a collapsing speed and a natural number that will give the dimension of the simplices, we obtain a group that is the moderately discontinuous homology group of dimension n at bits b, or speed b. Okay, and this depends on the metrics. Okay. Let's see the definition, and we'll see that it's very parallel to the singular one. So we have X subanalytic term, G an abelian group. What are the simplices in the theory? Since this is our singularity. So the simplices, since there is a conical structure that it's at the center of the object we are interested in, so the simplices are images of the cone over the simplex. This is the standard simplex, so consider the cone, and the simplices are mappings from the cone over the simplex to our singularity. Okay, and now we do the usual thing. We take the chain group. Okay, formal sums of simplices. We have the boundary map induced by the standard one. Okay, and then we have a complex chain, and we take the homology, and the homology is like the homology group for the parameter b infinity. We will see it that is a very coherent notation. And what measures this homology, as you can expect, measures simply the homology of the link, because we are just taking cones over the simplices, so this computes. Now we move to the parameter b. Okay, a real parameter b. Well, this is what I said. The homology group for the parameter infinity is the homology, the singular homology of the link. Now we choose speed positive, and now we identify 2 simplices if for every point their images are the equivalent. So if we have 2 B points, 2 simplices, one here, okay, and another here. Okay, we say they are B equivalent if for every point here, the image through the 2 simplices, this is B equivalent. Okay, if the image of these simplices in the set of B points here is the same. Okay, at the level of the B points here, the mappings are the same. Then we identify them. The boundary here, the boundary mapping also goes down to this equivalence relation. We consider first, the formal sums of equivalence classes of B simplices. The boundary maps goes down, and we consider the homology. And the homology is the moderately discontinuous homology group, parameter B. Okay, now we have extra structure in between these groups. Every time we have two speeds different, B2 less or equal than B1. In the same way, we have the 2 arcs that are B1 tangent of order B1 will be also tangent of order B2 because we have the same reasoning, okay? The same type of inequality. We have the two simplices that are B1 equivalent are also B2 equivalent. This goes down to this formal sums, and then we take the homology, and we have also an induced map on homology. Okay? And they are an important part of the invariant. So the invariant are all the groups for any N and B, and whenever we have two B's, we have this. So, a natural question: are all the all the speeds essential? Recall that we are working with subanalytic germs, so they are rigid, no? So maybe we can expect this B to be finite, etc. No? Or can there be an infinite number of jumps, whether this is not an isomorphism? So a jump will be a speed such that whenever you take something smaller and something bigger, then the isomorphism from the homology groups at speed B1 to the homology groups to the speed B2 is not an isomorphism. No? This will be a jump. So we'll see that when the considered metric is the outer metric or the inner metric, that in fact are the ones that we are interested in, for any subanalytic term, then we get that the jumps are rational and finite. Okay, and in fact the groups are finitely generated. Okay. Vale, let's see functoriality. So first functoriality that these groups have is for Lipschitz maps. So if we have a Lipschitz map, then equivalence of 2 points for the parameter B implies that the image is also big. Okay, this means that the distance of this goes to 0 faster than t to the b, and then you use the Lipschitz condition. And since you know, okay, this is trivial. And then you have this, and you can push also simplices and go to have the induced mappings at the level of the chain groups, the chain complexes, and you go down to the homology. So a Lipschitz map induces a mapping in homology. Okay. So, or in other words, the moderately discontinuous homology is a functor from the category given by the germs with the Lipschitz maps. Subanalytic germs with subanalytic metrics and Lipschitz maps. Another type of functoriality that is newer is by a B-map. A B-map is a new concept that gives very flexibility and computability to the theory. Let's see what is a B-map. So a B-map from X to Y is not even a function, it's a piecewise mapping. So it's given as a collection of functions its function in a set Ci such that the Ci's are a covering of X, okay, by closed subanalytic sets. And these mappings, you can think, for example, that are Lipschitz, to simplify. And we ask a gluing condition, that is that whenever we have two the equivalent points, and this condition, so these compositions are possible, then you have to have that the images are also be equivalent. So in short, these B maps define a well-defined mapping between the set of B points in X and the set of B points in Y. Okay, it's not a mapping, but at the level of B points, it is a map. Okay. So they are not continuous, but they are what we say moderately discontinuous. Okay, because the discontinuity can be only of order T to the B. Okay. So in particular, this allows to see that a B map induces a mapping at the level of homology. Okay, because it will go down to the chain groups of B simplices, etc. So here it is a drawing. No? For example, we have X, we have a covering in 3 colors, and for each piece of the covering, we have a mapping that you can think it is Lipschitz, sorry, and then for any point, for example, in the intersection, or at least that is RB equivalent, then you have to have that the image is the equivalent. The image is by, for example, aquí the blue one and the rose one are the okay. So maybe a more concrete example, if we have the surfaces I mentioned before, here we have that these 2 arcs were tangent of order 5, for example. Then we can collapse, okay, and this will be a B map. For example, these 2 equivalent points are sent to the same point here. And what about the possible inverse? The inverse is in fact a B map. The inverse is not well defined as it's not a well-defined map, but it is a B map. You can take this covering, okay, these 2 pieces, and send it here. For example, the image of this point that is in the intersection of the two sets is sent to the equivalent points. Okay, so, and if you take G and then you collapse with F, you take the identity. So since this is a B map, you can use that this is by functoriality. You have that at the level of the homology groups of the speed B, these are isomorphisms. Okay, so for the homology of level, these are this. Okay. We have a relatively homology and long exact sequence of relative homology. So we have exactly the same properties as in the classical setting with minor or not so minor modifications. Right? The homology of the point is as expected for dimension 0 is G, and for n greater than 0 is 0. We have a notion of homotopy, a metric homotopy family of Lipschitz mappings with the same constant. They all induce the same in homology. A family like that implies that they induce the same in homology. We have also a notion of bihomotopy, also in the same direction as before, as a B map. So we allow discontinuities of order T to the B. It's the mapping defined piecewise. Mayer-Vietory sequence. For this, we need to ask extra properties to the covering. So we have to ask what we call to be a B covering. So in order to have Mayer-Vietories, you need this short exact sequence. Okay, and bueno, we put the condition what we would need. For example, if you consider for points, you have to ask that what is said here. No, for every point P1 in U1, P2 in U2, ¿vale? Aquí, that when you look it here, they are the same, they have to come from something in the intersection. Because we ask that at the level of B points. Okay, so whenever you have 2 points that are equivalent in the union, then they have to have a representative in the intersection, and the same at every level, at every dimension. Okay, we ask that for every, whenever we have 2 simplices that are the equivalent. Okay, so let's see an example that is not okay, we come here again. So something that is not a B-covering is this one. Okay, this is not a B-covering because there are points here, one in U1 and another in U2 that are B equivalent and have no representative in the intersection. Okay, because the intersection here is here, and so there is nothing in the intersection equivalent to this point. But we can think of this mapping. Okay, this is right. Okay, here we have, as before, these points in the intersection that are in any of the in both of the open sets and are in fact have a representative in the intersection. Okay, so we have to take care of what kind of open sets we take. So once we have this, we have the Mayer-Vietoris sequence. We have a notion of B-connected components that appears when we look at the moderately discontinuous group of dimension n. So it's the group over the number of B components, and it's just we take x, the germ, decomposing irreducible components, so 2 are B equivalent if and only if there exists 1 point in x1 and another in x2. So we make a equivalence relation in the set of irreducible components, and we identify 2 if there are points that are B equivalent. Okay. For parameter B equals 1, as expected, we get information about the tangent cone. Once we consider the outer metric, because here the B points are identified whenever they are tangent. Okay, so one can look carefully and see that this is these are natural isomorphisms. And what about the homotopy? So the homotopy, what is an example, for example, of a loop for the parameter, a loop. Again here, pues a loop will be an image of the cone over the example of the segment. We have, of course, for a homotopy, we have a base point. Here we have a base point. So this loop is closed at the level of B points because the starting point and the ending point are B equivalent. So this will be a loop. It's not continuous, but it is moderately discontinuous. Okay. So this is the condition. And in fact, we allow discontinuities, as I told you before. So we ask this mapping, in fact, not to be continuous, but we allow discontinuities further to the B. So an end loop, pues will be defined. Will be defined from as in the general theory, it's a square, a cube, an n cube. So here we take cones over the cube that are given piecewise, etc. And we have the gluing condition. Okay, for any point in the intersection of the pieces, we have that the images are always B equivalent. So the image at the level of B points is well defined. We have a notion of B homotopies that works very well, and then we have a multiplication given simply by juxtaposition, as in the classical setting. And then we have the homotopy group that we denoted like this. Okay. Again, we have, for any 2 speeds, we have this this homomorphism connecting the B homotopy groups with the B prime. We have that it is abelian for n greater or equal than 2, as in the classical setting. It is functorial again for Lipschitz mappings, for B maps. Invariant by matrix homotopies, by B homotopies. For B equal infinity, we get the homotopy of the link. It is independent of the base point if the germ is deconnected. For the Seyfert-Van Kampen theorem, we need also to ask further properties to the covering. Okay, so we start with a covering by subanalytic germs, etc., by the subanalytic sets. We assume that U1, U2, and the intersection are deconnected. We choose a point in the intersection. And we have to ask the following. So we need this in order to be able to think as in the classical setting and reproduce the proof. Okay, so we need to ask that whenever we have paths, gamma 1 and gamma 2 in U1 and U2 that are B equivalent in X, okay, they induce the same mapping at the level of the points, then there is a path in the intersection that is B equivalent to both of them. Okay, so at the level of B, so the intersection works well at the level of B points. Okay. See that I am not saying that this is a homotopy equivalent, of course, because this will be too strong. Okay, this will be the theorem. And then when these are the hypotheses, then we have that the moderately discontinuous fundamental group is isomorphic to the amalgamatic product. Okay. So we have generalized this theorem to the more general setting of groupoids with a big amount of points. You can take an arbitrary set of points and find conditions for the covering similar to this one, so that you can obtain the moderately discontinuous fundamental group of the co-limit of the moderately discontinuous groups of the sets. Okay. We have a Hurewicz homomorphism from the homotopy groups to the homology groups. So an element in the homotopy is given, as I said, it is a B map from the cube, okay, given by functions defining pieces of a certain covering. And what we do is we refine the covering, finding a triangulation. We take a triangulation that refines the covering of the NB loop, and we compose the triangulation with the NB loop, and then we get a chain of simplices, of these simplices. Okay? So this is the Hurewicz homomorphism, and with this definition, we can prove that for n equals 1 is the abelianization. This is quite straightforward from the similar to the classical one. And to prove the isomorphism theorem, that is that if the homotopy groups are trivial up to order n, then the homomorphism is an isomorphism. Then we can only do it for the outer and the inner. So we really, well, we will see what happens here, and then it is, you will see how you can get this easy, okay? Because in these cases you can reduce it to a singular homology set. Okay? For beacons, we can compute beacons with the outer metric. So for B prime less than B, if we have a beacon, we have in fact that here all the points are B prime equivalent for every B prime less than B. So this collapsing mapping is a B prime map. Okay, a B prime map, and you can play as before. Here you take the inclusion, and then this contraction that I call, for example, F. So if I take the inclusion and then I take this, I get the identity. So this is an isomorphism at the level of B prime. So this beacon is like the point for B prime less than B. Okay, and for B prime equals B, one has to take care, and in fact you need to use all the Seifert van Kampen machinery to prove that in fact you recover the homotopy group of the link, and the same for the homotopy. Okay, this one has to take care here. It's not easy. For the outer metric, conjecture by left to right, also we see that the moderately discontinuous homology corresponds or is equal to the singular homology of the link of a B-Horn neighborhood of X, so an adequate B-Horn neighborhood of X. Okay, we have to choose B, and okay, so a B-Horn neighborhood is simply you have X, and for every, this is X, and for every X, we put a ball of radius, the distance to the origin, to the B, affected by an eta that is not very important. Okay, so this okay, neighborhood, okay, B-Horn neighborhood gives us the, okay, what happens here. The key observation is that if you have something that is B prime close to a point that is B prime equivalent to a point in X, then it will be necessarily contained in this B-Horn neighborhood. Okay, so you can compare the singular homology of this B-Horn neighborhood and the homology of X, the moderately discontinuous homology of X. Okay, using this okay. So in order even to compute the moderately discontinuous of the B-Horn neighborhood, you have to take care and use all the theory we have developed, the Mayer-Vietoris, etc., with a good covering, and finally you check that the homology for parameter B equals the homology of the link. Then finally, one can prove that the homology of X is the homology of the link of the horn with the horn is greater than B. Okay. For some B prime small enough, it has to be close to B, but close enough, but you can always, for example, think of B prime rational. So whenever it is rational, then this is a complex, simplicial complex. So it has finite simplicial complex, it has finite generated homology. And then in this way, we can see that the moderately discontinuous homology groups of germ with the outer metric are finally generated. Okay. And also we can see that there is a finite number of jumps, because if you study these sets in family, letting B prime vary, you see that this is a definable in certain minimal structure. You have Hart theorem, and you see that the topological type may only change a finite number of times, and this will be exactly the finite number of jumps here, where this topology changes. And we have also that the jumps where this happened are rational. Okay, why they are rational? This proof was given to us by Parusiński. For example, one takes, you have your germ X, you take this mapping from Rm to R2, okay, given by the modulus of X distance of X to our germ. Okay, and then where is the Berghoff neighborhood? So the Berghoff neighborhood is essentially the points where the distance of X to X is less or equal. And then the Berghoff neighborhood is obtained as the preimage of this this area, okay, in R2. So we have in R2, we take the graphic of eta x power b, and the preimage of this is the Berghoff neighborhood. Okay. Now we take this mapping, and by harsh triviality, there is a decomposition of R2 such that f is trivial over each of the pieces. Okay, so you have, see, and you have some decomposition of R2 that near the origin has to be of this type. No, there has to be some curves that separate the strata, so you can, since we have the description of the horns like this, the B's for which there is a jump, a possible difference in topology, has exactly the, since these curves are subanalytic, they have development like this, with certain are rational. So it is exactly the point, the B's for which there might be a change in topology has to be exactly the arc that appears here in the development of these arcs. Okay, so they have to be rational because these arcs are subanalytic. Okay. Bueno, we have mainly talked about the outer metric. The inner metric can be studied as an outer metric through this theorem that says that if we consider X with the inner metric, then there exists a subanalytic embedding that is Bilipschitz between our germ and the image with the outer metric. Okay. And well, moreover of X, the image is Lipschitz normally embedded. So for this germ, the outer and the inner metric is equivalent, but actually we don't use this part of the statement. And note that I want to say also that this F is in fact keeps linearly the distance to the origin. Well, in fact, it can be taken preserving the distance to the origin. Okay. So whenever we have an inner metric, we can take the image by this mapping and work with it as an outer. So, bueno, coming back to the initial examples, so homology of the complex plane curves. As I said, well, we have what we know, and we compute the interesting case, that is the outer metric, the plane curve with the outer metric, and what we get is the following. So to see what happens, one can think of the, we have X, and we can think of the carousel decomposition where we see, sorry. So we have a section where we can see the toric iteration, well, I guess all of you have seen this this picture where you have the torus in R3, and then you take a nested sequence of tori, so that you get inside the different, we say, approximation of your germ. Okay. This is a section, and This is the origin of my arc, my card germ. And okay, and now you study the homology of this with parameter b, for a parameter b. So if you take b, you have the development like this. So if you take b big enough, then you see the link without no identification at all. So the homology will be set because it is an irreducible plane branch. Okay. And when you take b smaller and you pass this, so you take b, for example, between b1 and b2. Okay. This is b1, b2. Okay, then you are identifying, for example, the corresponding step in this iteration. Okay, then what you get is also like S1. Okay, so the homology will be always set1, will be set. And when you consider the morphism between the homology for parameter b and for a smaller parameter b prime, is like the covering mapping from the, for example, here, the original one that gives three terms, okay, for every term when you identify the b prime points. Okay, so what I say is that the homology doesn't change, but this connecting homomorphisms gives you, as a kind of covering map, the values of b where there is a change that corresponds to the exponents that appear in the Teissier expansion. Okay, the Teissier exponents. Okay. Okay. So, so this is the curve case. So in fact, what we are recovering, then we are recovering all the information. We take the curve with the outer metric, we compute the invariant, the whole invariant, also these mappings, and we recover the exponents that are relevant where this collapsing happens, and we recover exactly the Teissier exponent. So the embedded topology is recovered not only from the outer metric, but simply from the moderately discontinuous homology. For the normal surfaces, we know the inner metric, we know this decomposition, the fixed in decomposition, and we compute the homology and the homotopy, the fundamental group, because we can obtain a covering, as I told you, a good covering to compute, for example, to apply, for example, the Seyfert's-Van Kampen theorem version for the groupoid, the moderately discontinuous groupoid, and we can take enough points, we can take a covering. So you fix B. For a speed B, there are some elements here that are relevant, some others are partially collapsed, and you take enough points in the intersection of all these sets, and you check that the open neighborhoods are good enough with respect to the hypothesis. We need to apply the Seyfert's-Van Kampen theorem. And what we also do is to construct a simplicial complex using this collapsing phenomenon for a given B that makes some of these species disappear partially. We use this. We can perform some real collapsing mappings that go to a simplicial complex whose homology, singular homology computes the B-homology of this surface. Okay, and why? Because the diagrams where this Seyfert-Van Kampen theorem, for example, is realized are completely parallel for the singular, for the fundamental group of this simplicial complex, and for the moderately discontinuous fundamental group of this normal surface. So it is okay. This is how we do. We just use this in order to construct the good P covering to be able to use our tools. And I think I'm finishing. The final result is that we also characterize the smooth point with the MB homology. So for the complex singularities. So if we have a complex singularities such that for the outer metric gives the homology, moderate discontinuous homology of the smooth point, then it is a smooth. And that's it. I finish here. Thank you.
Any questions?
I have a question. Maria, let me ask you the following. That for curves, you could estimate easily the homology in terms of the degree of the equation, right? But what do you think about the surfaces? So you have a surface in c to the 3 given by an equation. What do you think that, I guess that there is an estimate of the rank of the homology group or this kind, let's say moderate discontinuous homology group in terms of the degree of the equation. It's somehow quite usual question in topology, for instance, that when they like in the theory of Vero, Harlamov, Ittenberg and whatever, they estimate the configuration in terms of the degree. And could you have this something possible like this in terms of the degree of the equation, or in other, let's say in some other algebraic terms?
Oh, I don't know. Maybe the other way around, maybe trying to get the degree from the invariant, yes, but maybe, but I don't know.
Okay, let's say the rank of the group it just is somehow could be related in terms of the degree, so that if the degree,
for example, in curves, the rank is always 1.
Right.
So it's not here. It's not the group.
No, for curves it's not interesting, but for the surfaces it could be interesting. That it's definitely bounded, right? If the degree is bounded, then the rank is bounded, just because of the Mostovsky theorem of Lipschitz stratification. You have finite Lipschitz stratification, then finite number of Lipschitz types, and then the rank is bounded.
But you mean bounded by something cooked?
With something related to the degree.
Yeah.
Okay. And then you have plenty of invariants, like degree, you have, let's say, you have multiplicity, you have Euler number.
You can have several embeddings with different degree, no? Degree, you mean degree
of the equation. So that suppose we live in C to the 3.
Yeah.
And you have just one equation that defines your surface, normal surface, right? Mm-hmm. Then what could be, and it's clear that the estimate exists, but is this estimate, let's say, polynomial or exponential, so that you can just start from the complexity of the resolution graph in terms of the degree, since the thin-thick decomposition is somehow constructed by the resolution graph with some additional information, right? And then you could see what actually happens with topology. And then and this probably was done by some people like Nemeth. But when you just go to Lipschitz geometry, then it could be a reasonable question. Yeah. I don't want you to answer now. I just, I simply guess. You see?
Thank you for the question.
If there are no more questions, let's thank Maria again. Okay, it's my pleasure to introduce Javier de Bobadilla, who will talk about the asymptotic Lipschitz fixed point theorem.
Well, thank you very much for the invitation. It's a pity not being in Paris, but it seems that this situation is more or less getting over, and we'll have normal meetings again. I would like to apologize also for only showing up at this meeting now. So I was attending another meeting that I said previously I would attend, and also a PhD student defended her thesis this week. So I have a few obstructions for not being able to accompany you this week. So sorry for that. So I will build. So my talk will build on the talk of Maria Pe. So what I want to present is one application of moderately discontinuous homology, and the general problem is the following. So we want to locate fixed points, but sometimes a mapping. So you have some space. So the usual fixed point theorem, you have some space, you have some mapping, and you want to find conditions so that one point gets fixed. And this is important for many aspects in mathematics. And one of the important fixed point theorems is Lipschitz fixed point theorem that states that if the Lipschitz number, well, in appropriate conditions, if the Lipschitz number is different from 0, then you have a fixed point. But it may happen that what you have is some family of spaces depending on time. Okay, and you have a family of mapping, and it might happen that there are no points, so there are no fixed points. For any single, or you cannot ensure that there are fixed. This is better to say that you cannot ensure that there are fixed points for any single t. And now we let t, which we interpret as time, evolve in some interval. So we will and we will be concerned. So we will be interested in the asymptotic behavior when t belongs to 0. And the kind of problem that we try to solve is the following. So for simplicity and because this is what happens in the theorem that we were able to prove, I will think that the topology of the space xt is the same all the time. So you have some space xt, and now you have you fix some t, and you may have some point t that it doesn't get fixed, But what we would like is to find conditions so that there exists, when t approaches 0, there exist families of points such that the distance between xt and phi xt approaches 0. So this is what we call, so for this we will endow the space with a metric. So the space will be a metric space. And this is what we call an asymptotic fixed point. So in some sense, even if the mappings do not have individual fixed points, well, when you are using mathematics for nature, there is an error margin. So this theorem is as good as a Lipschitz fixed point theorem, because when you approach the time that you want to analyze, you will know that you have fixed points to any error margin. And in fact, we want to measure.
Do you suppose that your map is by Lipschitz, Javier?
Yeah, I for sure, I will state.
And you suppose that it is subanalytic, right? Or not?
Yes, if you give me a couple of minutes, so this is a general introduction.
Sorry.
I'll state a precise theorem. So, but you are right. Yeah, and you want to understand the speed of this evolution. Okay, so now we'll follow Lev's advice and give what is the precise version of the fixed point theorem that we do. So now I'm going to start with precise definitions. So you have the definitions. So a bounded family of subanalytic subsets is a subanalytic subset X that belongs to Rn times, and now you may write 0 plus infinity. So this coordinate is going to be called X, and you will regard the last coordinate as P. You ask this set to be bounded, and you consider the outer matrix. Okay. And now, so the next thing is a family of transformations. So this has a name, but perhaps I say the name as it might appear in the paper. So the paper is not. So we didn't choose all the notations, but probably the name is going to be. So let's see. Yeah. So now we consider phi x to x. We consider a subanalytic mapping, reserving P levels. Okay, so you see it as a family of mappings from xt to xt, and by Hart theorem, you can assume that the topology of xt is always the same, only the metric is changing. Okay, and you assume the following. There exists a uniform constant such that phi p is Bilipschitz constant. Okay. So So this is the setting, and now we want to state the theorem, and the theorem is the following. Oh, to state the theorem, you need to extend a little bit moderately discontinuous homology. So in Maria's talk, moderately discontinuous homology was defined for germs. Okay. So here you have a germ, and in a way, so you were taking a cone. Here we don't have germs, so we have a different situation. So T. So in the comparison with Maria lecture, the role of T lecture was played by the distance so we will think T as a kind of distance to the origin in order to define the homology theory, and in the case of Maria talk, there was only one point that has distance 0 to the origin, which is the origin, and in our case we allow the xt to degenerate in a subanalytic set, and the only condition that we put to the subanalytic set is to be bounded. Bounded, this is an important condition, at least technically for us. So we really use this condition. Okay. Very good. And in this situation, we can attach. We can attach to such a family the moderately discontinuous homology of X at some speed of X. In this lecture, I will talk about the outer metric, but there are some statements that work also for the inner metric. So you can define the moderately discontinuous homology. You can prove that it is so. For this talk, it is enough to take coefficients in a field of characteristic 0. So you can prove some functoriality for the mapping phi. And then once you have this functoriality, you can define the Bilipschitz number. So the B. The Bilipschitz number is the sum. Is the alternating sum of the traces of the action of P in H D I X U. Okay. So this is the Bilipschitz number of phi. And now the theorem is what you expect. The theorem says if the Bilipschitz number of phi is different from 0, then there exists asymptotic fixed points at SP B. So what is the meaning of an asymptotic fixed points at SP?
Sorry, Javier, what is the condition? They are distinct or different from what? What is the condition you wrote?
Ah, the Lipschitz number is different from 0.
Okay, thank you.
Yeah, the usual condition in topology, but in moderately discontinuous homology. And the meaning on an asymptotic fixed point at the speed 0 is the following. So it's gamma from 0 delta. It's a subanalytic map. Let me call it X to be big X such that the limit when t approaches 0 of the distance, the Euclidean distance between phi t of x t, and I have to say that this map is yeah, so this is in R n times 0 infinity, and if I project to 0 infinity, I send t to t. So this is a map that preserves t levels. Okay, so you have your analytic set, you have your x, and now you have your interval 0 delta, and it's something that looks like a section of this projection. Okay, so you have and you view this as a family of points in X. Okay, very good. And now the condition is that this the following limit vanishes. So let me write it here a little bit smaller. So you can ensure that phi of xt will be closer and closer to xt at a speed b.
Javier, can you put the camera closer to the blackboard? It's very tiny. You can approach.
That is difficult. So what I can do is to write bigger.
Okay, thank you.
But that would be complicated. So please let me know what you don't see, and you don't see the limit, I suppose.
Yes, that's right.
Okay, so let me write the limit just below with bigger letters. Please interrupt me if the quality of the connection or the quality of my writing is not good enough. Just stop me. I will repeat the picture and the limit. So this is x. This is 0 delta. And now such a family looks like a section. This is x of t, and x of t falls precisely in t. And now I transform by phi. This is phi of x. So this point is phi t of x of t. Okay, and I am measuring this distance. And the limit condition is okay. So this, so even if you don't know that you have a fixed point, up to up to distance b i's, asymptotic distance b i's, you really see a fixed point. So this is the content of the result. And now, so I see I have 20 minutes. What I want to do is to explain one application and to give some ideas on the proof. Okay, so if there is no complaint, I will erase this blackboard and try to say one application that is starting at this moment. So the application is to monodromies of isolated singularities, and I want to be very concrete and to speak on a particular class, but which is an important class of hypersurface singularities. So I will study functions So I will study sums of powers of the variables, and these are the Bristol-Fan singularities. And we have chosen them for two reasons. One is because they are important, so all these exotic structures, and so that they are very distinguished. So they have provided a lot of beautiful examples along history of singularity. So this is first reason, and second reason is that we can compute the Lipschitz numbers for these singularities in a fast way, and if we want to think in more general terms, then this is a new research topic that is starting, but we wanted at least to provide one concrete example. Okay, so you take a polydisk, or you take a polydisk. Okay, you have your singularity, and you take the mean of vibration in a polydisk. Okay, and now we want to associate to this a bounded family of subanalytic subsets. Then this is very easy. So I will call B, even if it seems like ball for the polydisk. So let me take B intersection F-1 of the open interval. So now you have the usual picture for the mean of vibration, and here you have the open interval, 0 delta. Okay. So this plays the role of our X in the theorem, and in this case, it is very easy to produce a T-preserving monodromy, which is uniformly by Lipschitz, because the monodromy that you produce really is an isometry. So you are going to send set I to E 2 pi I divided by AI set I. So this formula provides the monodromy. So we are in the setting of our paper, of our theorem, and now it is possible to prove. It is possible to prove that the Lipschitz number for certain B, and in fact, what is the B? So so you take the list of numbers 1 over A1, 1 over AN. So these are numbers that belong to the interval 0, 1. So they are all smaller than 1. And if B is smaller than the maximum then is different from 0. And you have approximate fixed points. So for yeah, well, in this case, you will have many fixed points. So so now this looks a little bit stupid because I am choosing a very concrete representative of the monodromy, but you have to think of the situation like you think in usual singularity theory. So the monodromy is unique up to isotopy. So this is a Bilipschitz monodromy, a Bilipschitz monodromy with uniform Lipschitz constant, and we can prove that if you have two Bilipschitz monodromies with uniform Lipschitz constant, then they are Lipschitz isotopic. And because of this, by homotopy invariance of moderately discontinuous homology, the Lefschetz number that you compute for this particular choice of the monodromy coincides with the Lefschetz number of any other element of the in the Bilipschitz mapping class group of the monodromy. So the content of our theorem is that for any choice of monodromy in the Lipschitz mapping class group, B fixed points will be present. Okay, under these conditions. So let me say that we did some precise computation for some cases, but so I take responsibility of any mistake here. So I relieve Maria of any mistake I can make for going a bit too fast, because but I am really convinced that the computations we did will generalize. But anyway, we will know this very soon, because now we are at the end of the writing of the paper. Okay, so and this is surprising in some sense because it was proved. So in the topological setting, or you only have, so the monodromy doesn't have to have any fixed point. So there were examples, I think, by so I think that I don't remember whether the first construction was by Le or by Acampo, but or by both perhaps. I don't clearly remember, but there are examples of monodromies that do not have fixed points. So even if they don't have fixed points, if you make the right representative of the monodromy, they need to have B fixed points, and at least for me, this is surprising and very good. Okay, so this is the application I wanted to show, and now I want to give some ideas of what are the main steps on the proof. So for this, I have 10 minutes, and it should be enough to convey the main ideas. Any question up to now, or any complaint? Okay. So the main steps for the proof. So there is a step 1. That consists in extending the theory conveniently. So let me explain what is needed. So our situation is the following. So first difference with Maria is that we have a bounded set, which is degenerating when t approaches 0. And it degenerates to some subanalytic set, which in the example of the Bilipschitz singularity was the central fiber, instead of a point. So in the setting that Maria explained, you just degenerate. So you are studying the conical structure and you degenerate to the vertex. Okay. This is one difference, but another difference is in the transformation. Okay. So you don't ask phi to be a Lipschitz transformation. You are asking phi t from xt to xt to be Lipschitz with uniform Lipschitz constant. And this seems slightly weaker. Okay, so this in principle doesn't have to imply that phi is Lipschitz, and if you want to use some kind of functoriality, you would need that phi is Lipschitz. Okay, so for this we introduce two versions of our theory. So let me explain what is a simplex. In the version of our theory that is closer to the usual version, you take a simplex, you multiply by 0 delta, and you send it to x by some map, and this map is LDA in Maria talk, which means linearly vertex approaching, and linearly vertex approaching means that if you take level t to a level that is 1 divided by c, so t of sigma of xt is smaller or equal than k t 1 over k t for a given. Okay, and now you define a B equivalence relation in these simplexes as Maria did, so I cannot repeat here, which means that two simplexes approach at a speed v, and you need some subdivision relation, so you do all the theory in the same way, and from this simplex you obtain a first version of the theory that you call moderately discontinuous homology of x and d. Okay, so this moderately discontinuous homology is functorial for Lipschitz maps, and it's functorial also for the B maps. So B maps are very important in our theory. Okay, and B maps from x to x are maps that are piecewise continuous and Lipschitz, and roughly speaking, in the overlaps, they differ by, well, here I have to be a little bit more precise. And if you have 2 points, in the sense that Maria defined it, if you have 2 points that are B equivalent, then the transformation by phi has to be B equivalent. Okay, so I have here functoriality for B maps. So this is version 1. And now version 2 is an innocent change. Version 2, you send the simplex, so So you change this condition by an equality. So to such a simplex you call a normal simplex, you develop the theory exactly the same way, and you obtain a second homology theory that we call normal, moderately discontinuous normal homology. So this dependently. Of course, a priori, this homology has different functoriality properties. So if you want functoriality for this homology, you need the map to preserve the levels, which is what happens to this map. And you have a notion of B maps. And the difference between the notion of B maps here and the notion of B maps here is that if you have 2 points, gamma and gamma prime are 2 preserving T-level points, gamma equivalent, B equivalent to gamma prime should imply that phi of gamma should be B equivalent to phi of gamma. Okay, so this is the normal condition. But what is important is that this condition is not the same to be a B map preserving T levels that a normal B map. So to mapping satisfying these conditions are called normal B maps. And in fact, the condition on a normal B map is weaker than the condition on a B map preserving T levels, because for normal B maps, you only have to check points that are T level preserving. And for a normal B map preserving T levels, you have to check all points. Okay, so you have 2 different homologies with different functoriality notions. And the one crucial step in our proof is the following theorem. Is that you have this equality. So this is one theorem, and the proof of this theorem is not entirely obvious. So I think I am getting over time. So can I speak for 3 minutes?
Yes, of course.
Fine. Thank you. Okay, so you have this theorem, and now the interesting thing is that phi. So it was not so easy to prove that phi is functorial for this theory, but phi is functorial for this. So in particular, you get functoriality of this theory by B maps and by maps that in principle wouldn't have functoriality for moderately discontinuous homology. The proof of this theorem is not entirely obvious. It proceeds in the same way that that you have to do to prove that the moderately discontinuous homology is finitely generated. Okay, so now let me explain how. So once you have defined the homology theory, the idea of the proof is the following. So you have your X, and now you define the horn of a speed V and some amplitude associated to X. And this is what you expect is the union of the points X t such that the distance from x to x is more or equal than theta e power b. And now, following a conjecture of Lie that was proved in our theory, we prove for both theories, but now let me be fast, that the moderately discontinuous homology at the speed d of x is the limit when t goes to 0 of the ordinary homology when b prime is bigger than b of the ordinary homology of the horn b prime eta, but it doesn't matter which amplitude you choose. Okay, and now we want to reduce our theorem to the usual topological theorem. So what you do? So you have your transformation. So I think it's easier now to picture this. You have your transformation. Fine. Okay. So now you take a horn, appropriate horn, and actually this limit stabilizes. So you can fix b0 bigger than b and obtain the equality. Okay, so you take such a horn of amplitude of a speed b0, and now you try to extend your mapping. Well, extending this mapping is not so easy. So we proceed in several steps. So the first thing is we want to project the horn to the set. So we take a projection of the horn to the set. That projection cannot be made continuous. So we need a discontinuous projection, but we are lucky, and this discontinuous projection, in fact, is a B map. So we obtain a B map. So we first project from the horn to the set, then we have the mapping defined into the set. And now, but we pay the price that the mapping that we have constructed is not continuous. It's a B map. And now we want to make it continuous. So in order to make it continuous, we have to deform and we have to make an interpolation procedure. When you make an interpolation procedure, you go out of the set to another horn of the same speed, but of more amplitude, 3 eta. Okay, and we want a transformation from a space to itself. So we have to shrink back the amplitude from 3 eta to eta. So for this shrinking back, we need a ballet by Lipschitz theorem, and for this reason, the maximal generalization that is possible for our theorem is polynomially bounded or minimal structures. And after using Ballet's theorem and some readjustment of the levels, because Ballet theorem perturbs the T levels, and so we have to readjust in some. So this gets a little bit technical at that point. Then what we obtain is a continuous mapping, preserving T level from the horn to itself, and this mapping is the same as a B map than the original mapping. Okay, now we use that we have ordinary homology in the B set. We take the new map that I call phi bar. I apply Lipschitz theorem, the topological Lipschitz theorem, in any level, and I obtain fixed points at any level. And now by card selection lemma, this gives the B fixed point that we are looking for. And this is the end of the talk. Okay.
Yeah, let me ask you something. That why this fixed point will be asymptotic to your more or less fixed point? It could be very far.
Sorry,
Right.
so let me
So
put the volume.
what do you get? You get the theorem of Lipschitz, right, on each level. Then you find the family of fixed points, right?
Yes.
Then you just use the arc selection and you get the fixed point as the R, right? But the point is that I don't really understand why it should be asymptotic.
Let me explain why.
Because
yeah, it's enough with this picture. So to each T level, you obtain a fixed point, okay?
yeah.
And now curve selection lemma gives me, but let me picture the fixed point here. So we are in the horn, so the fixed point need not to be here, okay? But really, I can assume by curve selection lemma and the standard fixed point theorem that phi bar of composed with gamma really equals phi bar. And now I miss
Yes, this is okay.
This is
Right,
okay.
but-
So now what you do? Now you project so-called gamma prime is the projection of gamma to x. Okay, so I was fast and I didn't say it. So you make the projection to x. Okay. And now you get the transformation, and now this projection doesn't have to transform into the same one. So you see this is this on the white line and this is not on the white line. So you have now now you have to compare. So now this gamma prime is your candidate fixed point. So what you have to prove is that phi of gamma prime is V close to gamma prime. But how do you prove this? You know that gamma prime is V close to gamma because this is a projection and this is the V form for V bigger than V. And now you have to use that the phi that we obtain is also a V map, and then this gives all the needed bounds. Does this solve your question?
Yes, yeah. Yeah, I was thinking that you will use another technique, like this kind of Mannion and Weinberger, let's say Fedor Mannion, that he just studied the number, the components of the homotopy types of the map, which are Bilipschitz maps. So that he probably, if I remember correctly, then he somehow proved that there is another map who is close enough to our one. Because, maybe it's another kind of idea.
It's more elementary than that. So
this one, it looks more elementary. I agree.
It's only using the. So what we like is that all these generalizations that appear in the moderately discontinuous homology, they are used. They are used in an essential way. So without B maps, we couldn't do. So it's impossible for us.
Right. And another question: do you expect a counterexample in non-polynomially bounded minimum structure?
I don't think so. The point is that, I think the proof is harder, but if I have to bet, so the only place in which we use polynomially bounded is to use
Valette theorem.
But perhaps by a detail by a detailed geometric analysis. It would be great. I'm not sure.
Okay, are there any other questions?
Yes, I have a question. Are you thinking about applications of this in the Lipschitz classifications of map germs? For example, it seems to me that looking at those fixed, not fixed points, asymptotically fixed points means that you are looking somehow at regions of the Milnor fiber. If you think of your example, Fambriscorn example, you are somehow looking at region, hornical regions in the graph, okay, which gives you a region in the Milnor fiber, which are fixed by the monodromy up to Lipschitz transformation. And I think that you are approaching some Lipschitz invariant of Lipschitz classifications of mappings of functions from, say, Rn to Rp, that's way. Because what you are looking for somehow is, you see, you give yourself F, as you did, say, from Cn to C, Fambriscorn, and you consider the graph P equals F, okay? And now you are looking for a kind of hornic decomposition of the whole graph, which will give you decomposition of the Milnor fiber, which will be fixed by the monodromy. And I think it approach what you are doing approach that. But
Yes.
maybe we have to discuss that later.
Yes, that is true.
Well,
So,
for example, do you have a relative polar appearing?
Sorry, polar. You said polar.
Yes,
Yes, indeed.
do you have relative polar curves appearing in your Fambriscorn example?
Sure. In the case of curves, I think we have some understanding, and yeah, polar curves will say everything. But what looks less known to me and very appealing is to do the via campo formula. Try to find the meaning. So there is many invariants can be generalized, and yeah.
Okay, let's thank Javier again. And we continue in exactly 5 minutes. Okay, it's my pleasure to introduce our next speaker this afternoon, Adam Parusiński, who will talk about Lipschitz stratification for real singularities.
Okay, thank you very much for the invitation, and I also would like to apologize. I will try to share the screen. It seems up. That I was not present before at this conference because there was another one. And the subject of my talk is the idea is the following. So for real singularities, and here I mean various classes of singularities, mainly semi-algebraic and subanalytic sets, or more generally sets definable in a polynomially bounded or minimal structure. The idea of construction, actually, it's I think there is one idea which is based on two observations. One is called L-regular decomposition, and the other is preparation theorem. So and preparation theorem. all of them actually were, both of them were born for construction of such stratification for subanalytic sets. And so I would like to do some kind of publicity for those tools, in particular for the preparation theorem. Actually, this is my fourth talk this week on the preparation theorem. So first, I recall briefly what is regular decomposition, because this is a meeting on Lipschitz geometry. So I believe it's not necessary to introduce a subject or even Lipschitz stratification. Maybe at the end, I will say a little bit about it. Actually, those two results can be used to study metric structures of singularities independently of Lipschitz stratification. So L-regular sets or L-regular decomposition, it's the following. So when you construct cell, like cellular decompositions for semi-algebraic sets, usually what you do, you take, you fix the system of coordinates, and then you construct it inductively. So you start with, let's say, one horn. Oh, this is actually already two steps, because this is one cell is just a segment interval on the line, and then there is this horn, and then you build the horn over it, and so on. And to get those L-regular sets, so this is inductive definition of this type, where B is one variable less but smaller. Actually, here it's a reminder of the old definition. So old notation. So actually, I should rather write x prime xn, and x prime are the first n minus 1 variables. Okay. So, and then when you talk about this cells in higher in some codimension, they are simply graphs. So, for instance, such a piece is such a cell, and they are called L-regular, L for Lipschitz, because you ask the partial derivative, first order partial derivatives are bounded. So those sets have many geometric nice properties. They have Whitney property with exponent 1, which means that internal metric and external metric, they are equivalent. For instance, let me give another example. You can show, for instance, I will give you an example of such a set. So you take three variables, and you suppose that x is between, oh, this will be open. Up here, y will be between x squared and x, and z will be between 0, up, open, and like this. And if D is sufficiently big, D, then actually this is such a L regular set. The derivatives are bounded, even if you have negative exponents. And actually using L regular decomposition and preparation theorem, you can prove that subanalytic sets, compact subanalytic sets, can be decomposed as union of such cells given by monomial inequalities, but with negative exponents. And this, you cannot get rid of this negative exponent, because when you compute the volume of the cell, restricted to a small ball, the leading term will be constant, and it will be, I think, D as far as I remember, but there is a logarithm of epsilon, which comes from 1 over y. So so these are typical examples of such regular cells. And the theorem says that any definable or subanalytic set, and also here is the reminder of the previous talks, in notation, that can be any set or finite family of sets can be decomposed, so it's a disjoint union of such L-regular sets, but maybe they are, for each cell you need a different system of coordinates. I mean, usually you need it. So the way those cells are attached, it's not as clear. And this theorem actually holds in arbitrary O-minimal structures. So for example, flat functions are allowed, and in ordinary polynomially bounded structures, you do not have a generic Lipschitz triviality, which means that you may have families of sets that the Lipschitz structure changes continuously because simply the exponent. So you take the set like this, and this would be, for instance, x to the power y, and because you can change both x and y, you can change the exponent, the order of contact changes. Now I'm coming to the preparation theorem. So the preparation theorem is something much more serious. So the first, it was introduced for subanalytic functions, and so it was in '94. And there is a very nice work of Jean-Marie Lyon and Jean-Philippe Rollin on this. And so for me, the reason for introducing it was to handle the distance using resolution of singularities. So this is a kind of maybe I will write it, kind of Puiseux rectilinearization, which is of course not as beautiful as resolution of singularities, but it has this advantage that you control completely one variable. So now the variables are, there is one distinguished variable, so that justifies this notation when I put x, this special variable y, which is fixed, which you do not assume any kind of genericity of it. And any function on pieces on those cells, which are definable, or here subanalytic, can be written in this way. So there is a part which depends on all the other variables, x, and so this is kind of a black box. And then this kind of shifted Poiseuille term, but only one term, which depends on variable y. And then there is a unit. And the form of this unit is extremely important. So actually, this unit can be written down like this. So there is a map which all coordinates are depends just on x, and what is important, it's in dependence on y. Y1 is this shifted y. And actually, how it is obtained? It is obtained by the resolution of singularities, some kind of blowing up, and maybe substitution of powers because of Poiseuille. And these are plays role of coordinates on this blow-up space, where our function is normal crossings. So actually, what you can do, you can iterate it and do the same for those functions on x. And you can do it for finitely many functions simultaneously. And what is important also, that this v function in this coordinates on the blow-up space, this is real analytic, non-vanishing because it's a unit. U means unit. And so invertible, and because the image of this map is relatively compact. The image is a neighborhood, it's a small neighborhood on a blow-up space. So this theorem replaces, in a way, resolution of singularities, but it allows you to control metric behavior of x, of f, with respect to y. And not only on f, but also of its derivative. Because when you differentiate, this is very easy to differentiate with respect to y, but actually this form allows you to say that this derivative up to a constant is bounded by f divided by y minus theta. Okay, so far so good. So this is this preparation theorem. And actually, there are, in the subanalytic case, there are two proofs which are a little bit different, but in essence, they are very similar. But there is another version of this theorem, which is in a polynomially bounded or minimal structure. Anyway, the theorem cannot be held, of course, in the structure which is not polynomially bound. And this theorem was obtained by Van den Dries and Spijsegger, and the proof is by model theory, and that's actually, it's non-trivial. It's highly non-trivial. This is a geometric translation of a property which is called valuation property, which was obtained by Van den Dries and Spijsegger after many I mean, long work by Van den Dries and at least three papers. So I'm unable to tell you what is the idea of the proof, modulo that you have to, in a way, prove it for some curves or valuations, which is possible, and then to use a model theoretical compactness. So it's a very interesting that this theorem can be proven either by some approach based on resolution of singularities, which is rather closer to Jung's approach to resolution of singularities from on one side, and on the other side using this model theory. And actually, this version, original version, it's not exactly good because there is no information about the unit. So unit is called U here. I mean, no information besides this one, that it's a unit. And for instance, this does not allow to control the derivative with respect to y of f. But this was recently, a few years ago, improved by Nguyen and Valette, who using the original theorem of Van den Dries and Spijsegger, so there is, for f, but also for its derivative, df dy, they proved the theorem with extra information about the unit, which is more or less similar to the information we had before, except that there is no way of saying that this function is analytic. So it's only C2 with bounded derivatives, first order derivative on the neighborhood of this function. Okay, and this theorem has many consequences, and I'm interested in the consequences for Lipschitz property. So let me state some. People who were in Lumini recognize something. So the first property is the property which looks easy, but it's not as easy. So if you have such a function, you can think subanalytic function. It's already non-trivial, definable. Then exactly its derivatives can be bounded by f divided by the distance to some set which is of smaller dimension. So as I explained on the previous slide, one derivative, when you have this beautiful form preparation, can be bounded by the distance to the graph to this translation function theta. So this is, of course, how you prove it. Okay, and actually, in a way, this is better theorem. Of course, theorem B implies theorem A, and this is exactly what I told you, that as soon as you have such a function with this distinguished variable, then it's enough to bound only this variable, but then the distance is bounded in direction y. So what I mean by this, I mean the following: that you have x, which would be now single variable for the reason, and you have this set x, which can be complicated, even singular. And then when you take a point, Oop. Maybe let me draw a little bit different example of this X, like this. And then when you take a point, the distance is very close, but the distance in direction Y can be much bigger. So this inequality is stronger. But thanks to this property behaves well, and also with respect to parameters. When you have a parameterized functions, extra parameters, still you may construct such a set, and the constant would be universal. Okay, so far so good. And now I'm coming to the main ingredient for the proof of the existence of Lipschitz stratification. It's kind of generalization of theorem A. Okay. So what really happens here? It happens, so maybe motivation for this theorem first. Assume that you have two leaves. Like two cells. Over one of them. And now what I would like to have the following properties. When I take the Lipschitz vector field downstairs, and I lift it, if these are graphs of functions, the lift is unique, I would like the lift to be Lipschitz. As well. And to do it, let me write those leaves as the graphs of two functions. I used before maybe eta 1 and eta 2. So one of the property you need that when you take two vectors in the lift which live on the same over the same one, so it will be so this is the component, this vertical component of this lift, that it's bounded by the distance between these 2 points. So this is exactly the statement of the theorem for F equals. Then there exists a stratification, it's a stratification. I do not claim any properties of this stratification, such that any Lipschitz vector field tangent to strata with Lipschitz constant L lifts to a Lipschitz vector field with a constant which is controlled. I said how to compare 2 points which are over the same point I need also the property that eta1 and eta2 have bounded derivatives. First order. So the projection of each leaf over this base is by Lipschitz. If this base is L regular, which you can assume thanks to the theorem, and of course there is Lipschitz on one of them. I have to apply this theorem not for to the derivatives, let's say, of eta I. How do you? I said that it's a generalization of a theorem A. This is because if we take the union of strata which are not open, this is a set of smaller dimension, and just when so if you have X like this, and you have a point away of X, and you take, let's say, the unit vector field, you can extend this vector field to a Lipschitz vector field which vanishes on X with a constant one of the distance of this point to X, and apply this theorem C to theorem A, but not B, to this Lipschitz vector field. And because of universal constant, you can and you get the result. And how you prove it? You prove it in the same way as theorem A. What I explained, you just differentiate. But you need something extra. You need that the translation function, which was called theta, have bounded derivatives. So that's really why for the proof you need to use a preparation theorem and also a regular decomposition. And now when you have this result, the construction of Lipschitz stratification is fairly standard. So let me recall what is Lipschitz stratification. So my notation is the following. I fixed a set, which is a subanalytic. I prefer to express stratification by filtration by skeleton, not by strata. So now the differences are non-singular of pure dimension K. Indefinable case, non-singular would mean for me C2 manifold. In subanalytic case, analytic, and which satisfies uniform extension Lipschitz vector property. What does it mean? It means that if we have a Lipschitz vector field tangent to strata, there are no other, on a set which is between two skeleta, then it can be extended to, or this doesn't matter, at least xj, because x sub xj, when you extend to xj, then you use this property and extend to x and then extend to Rn. But let me write xj. in the way that it is still the extension is Lipschitz. It's uniform. So Lipschitz vector field with constant Lipschitz constant L. And this would be like C times L, Lipschitz vector field. And there exists C which does not depend on, it depends on your X. Maybe. I mean, it does not depend on the vector field or the Lipschitz tangent also to strata. This is not the original definition. If I have time, probably not. How much time I have? Hmm?
5 minutes.
5 minutes, yeah. I can recall the original definition, which is a little bit like Verdier condition or Whitney condition definition of distances between the tangent spaces. But this, the other one has some advantages. You see that the conditions are in a way definable, because from here not. But this is more convenient for the proofs, and the proofs goes actually this way. This proofs which I'm going. So it's when you talk about the proofs. So it's a subanalytic case. So it's any compact definable or a subanalytic subset of Rn admits a definable or subanalytic in the same structure, Lipschitz stratification. And for subanalytic, the proof is, this is in this paper from 94. And for definable in polynomially bounded on minimal structures, there are two proofs. So one proof is by Nguyen and Valette. And the other is by Chalupchok and Yin. And this two proofs goes along the same lines, which at the end I will say. Briefly. And this, the third proof, which goes through non-Archimedean geometry and those non-standard models, looks different. But actually, it is based on the analog, or actually the same theorem of theorem A. This theorem which bounds the logarithmic derivative with y by 1 over the distance to some set, stated and proven using model theory. Of course, this theorem follows from as well from preparation theorem of Van den Dries and Spijsegger. So, outline of the proof. Okay, so this was this remark which I said. So, it's fairly easy. It's just a standard construction when you have these two tools. So, extension without condition of stratifiability of vector fields, any function, Lipschitz function, or any vector field can be extended. even with the same constant, which for vector fields is not trivial. So when you have a set of maximal dimension, you just stratify it to dimension one less, but because afterwards it's trivial. And then, so you can assume that the set is of dimension smaller, and then fix the set and use induction of dimension on J of this place you would like to extend in the, maybe I will show, this J. And also by induction, you see that it's only J equals D is matters. And then there is nice trick which was written in the paper Nguyen and Valette, that you decompose the set into separated towers of L-regular sets. So it's enough to, a tower of L-regular sets, it's something which I drew using those leaves, but maybe more than 2. And then use this theorem C to extend Lipschitz vector field on such a tower. So actually you project them, extend inside, because here is the highest dimensional, there is no stratifiability condition. And then you lift it using theorem C. Okay, and now as a bonus, Mostowski's conditions, which are satisfied for some of the points, which are called chains. So let me finish.
Okay. Any questions?
Yes, I have a question.
Bernard?
Is there any chance that there is a minimal such Lipschitz stratification?
Yes. Actually, when you change the definition, which will be weaker than this one, I think there is a chance. Yes, I think it is, but it's actually, I think that it's also this construction maybe should be, I really thinking that this construction should be understood from the point of view of this non-Archimedean geometry, and then maybe this provides an answer. What does it mean? Correct answer. Such kind of minimal or canonical stratification. Yeah, so it's like, I mean, you can think about this geometrically, because like you take the field of Puiseux series as your non-Archimedean field, and okay, so I think it is possible, but of course there is no result at the moment. But I think maybe the approach should be a little bit changed to understand better.
Okay, thank you.
Okay, it's my pleasure to introduce André Belotto from Marseille, who will talk about metric geometry of complex surfaces, Lipschitz normal embeddings, and polar exploration.
Thanks a lot, Tony, for the introduction. So as he said, I'm going to give the third lecture on a mini course, a joint mini course with Lorenzo Fantini and Ian Pichon. So it's the third part of the metric geometry of normal embeddings and polar exploration. So I'm going to treat the polar explorations part. And before starting the talk, I just want to, I know that this is the last talk of the conference. I think it's the last talk of the conference.
It is the last one, yeah.
So people might be a bit tired. So I also did not want to be overly ambitious, but still I wanted to be a little bit ambitious. So I'm going to try to talk about what is the problem that we're interested in. And the idea is to try to explain why true form, why the differential forms are important here. So I'm going to try to give an overview of the proof and concentrate myself with examples in the part that I'm going to talk about true forms and why they intervene. So that's kind of the plan for today. So these are, at least the main result of today is going to be in a collaboration with Lorenzo Fantini, with Andrés Demetri and Pichon, that you'll see here. If you've seen it, I know you all know them, but it's good to have their picture in mind. So let me start by a quick preliminary. So like, I know that my collaborators already talked about this, and both Lorenzo and Nang, they are terrific speakers on this, and I'm sure that they introduced this much better than I can. So I decided that I will I picked up parts of the slides of Lorenzo and Nang, and I made a preliminary so that we can all have, and hopefully this is going to activate the memory in everyone so that you already seen this. So we're going to consider here a complex surface germ with isolated singularity. At some point it's going to become normal. And I recall that there's a topological classification in the sense that given this a minimal good resolution, the weighted dual graph, so you see here, yes, the weighted dual graph is equivalent to, let's say, the topological type, which we can just say like this in a kind of vague way, which is equivalent to the homomorphism class of the link of X0. So this is going to intervene a little bit later on when we talk, when we state the main result. So just to have in mind this kind of topological time equivalent with the link. And if we consider, we can always consider locally some local embedding of X0 in Cn and consider linear projections. So either projections over C or over C2. And here we can parameterize them via the Grassmannian. So I recall that if I take the kernel of the linear projection here over C, then the intersection with X is what we call a hyperplane section. And generically, this is going to be a curve. Moreover, for the projections over C2, then outside of the singular point, this is an application between smooth spaces. So there is a critical locus, and we can always, so this is restricted to X, and we can always take its closure so that it's also defined with a singular point. So this is the polar curve. And a very important characterization for us, that I'm going to follow it for the entire talk, is that, well, if I take all of this projection of the hyperplane sections parameterized by the Grassmannian, then there exists some open dense set, even Teissier, that where this family is going to be equisingular, right? So what does this mean? It means that it can be resolved by a point blowing up. So after a point blowing up, every one of these hyperplane sections are going to be, point blowing up here is the blow up of Cn. So it has the resolution has to factor through the blow up of the maximum idea, which is exactly this guy. And this is how I'm going to denote it through the talk. So at the end, all of these hyperplane sections, the ones that are in this open set, are going to be smooth, and the family has no base points. In the same way, we can do the same for the polar curves, and in here, it's going to be related to the Nash transform. Now, I recall you that, oops, I cannot see because of Zoom. I see now. Okay, little technical issue, probably solved. Okay, so now considering a resolution here of X0, we are going to define what we call the L and the P vectors that I think that Anna has already defined in our talk. So given a generic hyperplane section, so generic in the sense of the previous slide, we can consider the intersection between the strict transform. So the star here is always going to denote strict transform for us in this talk, and EV, which is one of the irreducible components of V, where this V depends on the vertices of the graph. And we can consider the full vector that we have here, that we are always going to be in red. And this is something, it's a vector over the number of vertices of the graph. In the same way, given a polar curve of a generic projection, we also define the same thing. We take this strict transform, we intersect with EV, we look at this number, and we consider the full vector generated by this. So kind of the main object of today's talk is this triplet given by the resolution graph, this vector L related to the hyperplane sections, and the vector P related to the polar curves. Now a remark, again, trying to activate what already have been done in other talks. So I'm presented a very nice example, which is in the special case that the resolution is factoring through the point blowing up in the Nash transform. So in this case, all of these hyperplane sections are going to be separated. They're going to be smooth. They're going to hit the exceptional divisor transversely. Well, not all, but a generic one. So we can count them as arrows, right? And she gave an example where she made a resolution graph and counted the number of red arrows and the number of blue arrows in the graph. And she explained that. But in general, we don't talk about arrows because exactly we do not have these properties. We don't have it for free, and this is going to play a role in today's talk. So now let's start. Let's jump in to the polar exploration. Let's start our part now. So what is the motivation behind it? Where does it kind of come from, or where did it motivate us from? It comes from, we do know that there are two ways to resolve singularities of surfaces. So there's a classical result of Zariski that you can do it by via point blowings up and normalization, and the result of Spivakovsky almost 50 years afterwards via Nash transforms and normalizations. So we do recall that point blowings up is related to hyperplane sections in some way, and the Nash transforms related to the polar curves that we just saw. So there is a question that comes back to Leduntrang here that asks, are these two methods dual? And of course, this question have very many ways to be formalized in some other way. And what we are interested in formalizing with is in respect to the triplet that we've been talking about. So here's kind of two questions that arise for us. One of them, Anne already talked in her talk, which is, can we find special classes of surfaces for which the triplet is determined by the topological type? So can we find some special classes? And the second one is, does the topological type restricts at least the possibility of these triplets? Can we via the topology, at least have, I don't know, bounded or some more information about this triplet, and therefore about the relationship between L and P. Now, a first result in this direction, which kind of motivated is the result of Spivakovsky in the same paper, where he shows that if the surface term is a minimal singularity, which I'm going to define in the talk, but some special class, then the answer of one is yes. That is, the topological time does determine the weighted dual graph, and here there is the word minimum, right? So I do need to talk about minimal all the time. Of course, there would not exist a unique dual graph if we don't talk about minimal. So this is kind of an important thing throughout it. It's going to appear throughout the talk. Resolution that factors through the point blowing up and the Nash transform together with a unique triplet like this. And I do recall that Anna also already talked about a result of ours in this direction. So a result with Lorenzo and Anne, with Antoni and Pichon, that also answers question one and generalize the result of Spivakovsky because we talk about LNE singularity. So Lipschitz Normal Embedded, which I recall, minimal singularities are always Lipschitz Normal Embedded. Lipschitz Normal Embedded is a class of singularities which is bigger. So we do also give a positive answer to this question. And I just want to remind, to fix kind of the notation that I'm going to use throughout. So instead of saying that in a vague way that I'm going to fix the topological type, instead of that, we'll start with let M be a tree manifold. And we're going to say that there are things which are unique. And at some point, we're going to say X0 whose link is homomorphic to M. Okay, so this is a way that we are having to fix the topology. And in between them, we're going to say that there exists a unique triplet where gamma is a weighted dual graph, L and P are vectors, such that for any Lipschitz normal embedded normal surface singularity, whose link is homomorphic to M, so that's how we are fixing the topology once again, then the triplets are equal to this. It's the real triplets, where this guy is the minimal good resolution, which factors through the point blowing up and the Nash transform. So again, it's a unique way to give this answer. And I'm going to come back of this in the end of the talk, but I'm not going to talk about the main technical tools for now, because the main objective of my talk is actually to talk about question 2. So the question 2 is, does the topological type restrict the possibilities of this triplet? And here, once again, let M be a real manifold. The link of X0 is homomorphic to M, so we're fixing the topology in some way. And in between that, what we're going to say is that there exist finitely many triplets like this, so relations between L and P, such that there exists a normal surface singularity, and this triplet is realized by one of these finite number here. So the triplet coming from this surface singularity is realized, normal surface singularity normal. It's important in our hypothesis, is in between the finite number that we've scheduled, that we talked here, where again, this is the minimum good resolution which factors through the point blowing up and the Nash transform. Now, the steps of the proof and where I'm going to concentrate myself is the following. So we're going to start with gamma, the dual graph of the minimum resolution. Take it. The first thing that we're going to do is to bound the multiplicity of M of X via the topology, via this graph. Then we're going to bound the vector L. We're going to then bound the number of blowings up that is necessary for P to factor through the point blowing up of the maximum ideal. Then we're going to turn to the bound of the vector P, and this all are done, we're going to see, I'm not going to spend so much time, but the part that I really want to talk about is the last one, bounding the number of blowings up that factor through the Nash transform. So I'm going to spend, to change a bit. I'm going to spend a little bit more time in this point here. This is kind of my objective. This is where the differential forms really intervene. This is my main point. Okay. So first of all, how do we bound the multiplicity? So we have a proposition that is going to say that given a dual graph, there's going to exist some number such that the multiplicity of x0 is going to be bounded by this number that only depends on the graph for every normal surface singularity, which meets a good resolution, whose weighted dual graph is this one. And I don't want to spend too much time in talking about the proof, but I want to give you the main ingredient of it so that we visualize what we actually need here. And what we need is some way to produce a function over the graph with nice properties, and that only depends on the topology. And it turns out that in the literature, there's a very nice result that already gives us that, which is a theorem of Colbert-Métier-Pompesco-Pampou, very nice result. Which says basically the following. So we take a dual graph here, we fix a dual graph, and we're going to take some effective divisor. So let me just recall, by this, I mean some sum like this, where these dv's are bigger or equal to 0, some divisor over the graph. And we're going to assume some conditions over, like conditions that only depend on the graph and on D. And well, if you know a little bit, like there's a risk, okay, so what I want, the way that I want to think, if you know what this, a little bit of intersection theory, you know what does this imply, but if you don't know, I just want to, for the talk, to keep it with the idea that for sufficiently big D. Let's say this is an imprecise thing, but I don't want to really spend too much time talking about what this condition is. I just want to think that for a sufficiently big divisor, something good is going to happen. And what is the good thing that is going to happen? So, is that then for every normal surface singularities and every good resolution that has this dual graph, there exists a real function, a function in the analytic structure, a function in the maximal ideal, with an isolated singularity that's 0, and such that, so what does this notation mean? This one is the divisor related to the pullback of F. This is a strict transform. And this guy is going to be equal to this big divisor D. And moreover, this strict transform is a normal crossing divisor with X pi. So note that this is not a trivial result in many ways, because we're not supposing that this resolution is yeah. Okay. So why is it also interesting for us? We are not supposing that this resolution factors through the blow up of the maximum ideal, and therefore the hyperplane sections might be singular. All of them might be. A generic hyperplane section might be singular after this resolution. So up to taking like big powers, big orders D, we can find a real function in the structure whose pullback has normal crossings with the divisor. And this is the main ingredient. After we have this, we cook it up and we prove the proposition. So I just wanted to have it visualized here. So via this, I can bound the vector L in kind of straightforward way. So this is just the statement of the theorem, but just for the vector L. And why is that? I'm sorry. Because now we know by Weierich that the sum of MV times LV is smaller or equal than the multiplicity, which we do know that is bounded by this bound that only depends on the topology. So we can now bound them. At the same time, we do know how many point blowings up we need to factor through the blow up of zero, of the maximum ideal. And why is that? So what is the reason is that if we take a blowing up over a base point of the family of generic hyperbolic sections, then this sum that is here is going to increase. And I actually want to talk a little bit about this. I want to see this in an example so that this is going to also prepare us for what happens next. Because the idea of what we want to do next for the P vector is going to follow very similar to what we're doing here. But we're going to see that it's not going to work with functions. We're not going to have to pass to forms. So I first want to talk and see an example of what this is happening. Okay, so of course, if we can prove this, then we limit the number of point blowings up that we need to factor through the maximum ideal because, well, we are still bounded by the original topology. Okay, so what is the example that we're going to consider here? So consider a good resolution. Let's even simplify. Let's imagine that our surface is a hypersurface over C3. We're going to take some vertex, oops, there are some typos, and a free point E and V, and coordinate systems x, y, centered A, where x equals 0 is the exceptional divisor that we're interested, and Z1, Z2, Z3 are just centered at C3. MV is going to be the multiplicity of x0 along EV, and let's take a nice looking normal form, this one here. So Z1 is equal to x mv y, Z2 x mv y plus x, etc. here. So if we look at this, we take our point A, then what are the hyperplane sections, right? So the hyperplane section, which I read, is going to be given in here. You see, there is the multiplicity kind of everywhere. And the first one, Z1 equals 0, is a hyperplane section. So this guy here, let's say L1. This is just Z1 equals 0 inter X star. And the other one here is, for example, Z2, which becomes Y plus X. Z2 equals 0 inter X star. And notice that Z3 is not generic. Z3, I took the normal form in such a way that it's not going to be generic. And combinations of these are also going to give us. So we do have a base point. We have a point where all of the hyperplane sections that we take are going to pass through it. So this is a base point, right? And now, oh, and let me also notice that LV in this case can be easily computed. Oops. LV is equal to 1. This is just the intersection multiplicity of one of these curves with EV, so it's just equal to 1. Now, after the blowing up, what we're doing here is just taking x, y, x tilde, y, x tilde, like this, taking this chart. So we're going to have our EV far away, and now the new component, EV prime. And now, after doing this, we see that in a simple way that the two polar curves, hyperplane sections are now separated. So we resolved it. Let's call that one. We now resolve them. Once again, it follows in an immediate way just by the expressions that LV prime is now equal to 1. And the point is that when we blow it up, this base point, the multiplicity increased. Oops, not this. The multiplicity increased. Right. So to say MV, LV is of course is smaller than MV plus 1 LV, and this is just MV prime, LV prime, because now MV prime is MV plus 1. So there you go, this is the proof of the previous result. We saw what increased here. Okay. So now let's move on to bounding P. So let's just recall where we are. We want to prove this result. So this is the theorem again. We fix this M, we fix the link. But now we can put ourselves in a framework where L is already given. So what we can do is that we can fix actually a pair here, because we know that there's only a finite number of pairs like this. and a normal surface singularity such that, again, the link is M to M, we're fixing the topology. And we do have that this is the pair that we are considering, where the resolution is the minimum good resolution, which factors through the blow up, the point blowing up, the blow up of the maximum ideal. So in this case, now we want to, again, first bound P and then bound the number of blowings up to factor through Nash. So bounding P, we might imagine just as before that what we need is to bound the multiplicity. And in here, it would be good to bound the multiplicity of the polar curve. And we do have a nice formula to do that. So we do have the formula, the Legros-Teissier formula, which is going to intervene in an important way here. So since we factor through the point blowing up, we actually know that, that the polar multiplicity is going to be equal to the sum of MVPV. So in this case, by the Legros-Teissier formula, we know that the polar multiplicity is just the usual multiplicity. So this one, we do know that it's bounded by M gamma, so only depends on the topology, minus the characteristic, the Euler characteristic of the Munich fiber of a generic linear form. And since once again, it factors through the point blowing up, we can actually compute directly over the resolution graph how much this Euler characteristic is, just by using topology, techniques with the fiber and usual techniques, that it's only going to depend on M, on the multiplicity, which we know is bounded. We bounded MV times LV, so we bounded M. Only depends on information that come from the graph, the valence of the graph, the genus, it is attached to the weighted graph, and the L that we also have fixed by now. So this is all fixed, bounded, sorry, not fixed, bounded by gamma L. So the conclusion is that we only have a finite number of vectors. Oops, little typo here. Okay. Now, if we're doing this, let's just try to do the same thing that we did before with an example and see, okay, so things should do better. We now should just need a finite number of blowings up to factor through Nash in kind of the same way. So why does it work? So consider a good resolution just as before, C3. So I should have the same typo here. We fix a vertex, not the same. We take a point and coordinate systems just as before. So here's 3. So some typos survived. And in here, let's take an alpha V, which is bigger than MV. This is not going to play a big role in a priori here. But what takes a big role here is this N. So I'm going to take an arbitrary N, and I'm looking at this normal form that is here. So the thing that I want to remark is that this normal form, like I want to compute the polar curves associated to this guy. So a first information that we have here is that the multiplicity is equal to MV. So this is the first information I want to point out. The second information that I want to point out is that, so this is the V. This is my point, or point. Is that there's no hyperplane section passing through this point exactly because this is MV times 1, or 1 over MV, that I did just to simplify computations. So therefore, there's no hyperplane section, but there is going to be a polar curve. So one of the generic polar curves comes from the projection of Z1 and Z2. And as follows from the talk of Lorenzo presented this, one way to compute the polar curve in this case is by taking the pullback of dZ1. Oh, what happened? So, okay, so I'm going to pull back dZ1, dZ2. And what I'm going to get if I compute this guy is that, oh, no, I cannot see you. Okay, so now what I'm going to get is simply X. And if you make this computation, this is what you get, MV plus alpha V minus 1. And here it's going to appear, because that's what I chose to appear, X to the power 2n. And this guy is the polar curve. So this polar curve, it looks like this. Okay. This is our polar curve here. And I want to notice that the intersection multiplicity of it, PV is equal to 2. You can compute it in an easy way. It's the intersection of y squared minus x to the power 2n intersected with x equals 0, so it's just equal to 2. Okay, it's just equal to 2. And now we make the blowing up just as before. And we might once again compute the transform of the polar curve. So in here, we're going to take the pullback, let's call it P tilde, once again of dz1, dz2. And just by computing via this normal, this expression here, which is just the pullback of that expression of the normal form, what we're going to get is x tilde mv plus alpha v plus 2, y squared minus x 2n minus 2 with tildes, dx tilde, dy tilde. And once again, this is the normal, this is going to be our polar curve. Again. Yes. And the PV is once again, PV prime in this case, going to be equal to 2. So why is this a problem, right? The problem is here that I want to, in the number of blowings up to resolve this polar curve that we have here is equal to n. I need n blowings up, and I never bounded it. So I need to find a way that through the topology, I can bound this number n in some way so that I only have a finite number, because here I'm getting n for any possible n. So the topology should be able to bound this number n for this expression here. And if I look at it, the PV does not change, and the MV did not change, the multiplicity did not change. So I need to start searching something that does change in this expression. And the thing that does change is coming from this part, if we see here, in which we can identify via the differential form that is coming from here. So this motivates us to now look at the true forms and to look at invariants which are going to depend on the true forms that are attached here. Okay. Other questions? I cannot see you guys anymore. Okay. Okay. So let's move on to talk about this differentials and what we're going to do with it. So we're going to consider the sheaf of Kähler differentials, but don't worry, I know this is the last talk, so I'm not going to do this technical. Actually, let's just look at a simple and elementary characterization of it. So I'm never going to define what this means here, just so people know it's not the reflexive differentials. So we're not just taking the differentials outside of the singular set and taking its dual, its double dual. What we're actually doing, well, the characterization for the talk anyways, is going to be the following. We're going to consider the embedding that we're used to, some coordinate systems, and we recall that the true forms over Cn are spanned by these true forms here, dz1, dz2, etc., dzi, dzj for all of them. Now consider a good resolution of singularity. So here again we have a sheaf which is, sorry, the sheaf of differentials is again easy to define because this is smooth. Then what I'm claiming is that the following equality is true. If I pull back, and this is the equality that I'm interested in, if I pull back all of the true forms over Cn, this is going to give us the same as the pullback of the sheaf of Kähler differentials over X. So this is kind of what I want to use during the talk, and it's actually everything that we actually need to use in the paper too. And these are going to give us subsheaves of the sheaf of true forms over X pi. Okay, so as Lorenzo talked about in his talk, we can define here what is the matter discrepancy. So the matter discrepancy, I think Lorenzo talked about the log matter discrepancy. It really doesn't make, for surfaces like this and for the volume form, it's just arithmetics. It's not really important. So the matter discrepancy, well, in the case that we're looking here, which is local tree. Okay. After all of this regression, the matter discrepancy is simply the order of the sheaf that we pull it back along the exceptional divisor V. So in order to make this concrete and to see why this is what we want, let's use the same local form that Lorenzo did in his talk. So we take some 3 point A in EV, just as before in our example, and the coordinate systems just as before, with EV equals to X equals 0. Now, if we take a generic guy in between the omega 2 Cn, say the last example was dz1, dz2, and we pull it back, we're going to have this kind of normal form where this term here is the matter discrepancy, and this F is nothing else than the polar, or the strict transform. Transform of the polar. And this is the term that we wanted. So if I just come back to the previous slide, you're going to see that this was the polar, and this is the matter discrepancy. This was the polar, this is the matter discrepancy, and this is the term that really changed. Okay, so now we are relating all of this. What we need with the Kähler differentials, we can go to the kind of the main technical result of the paper, or not of the paper, but the multiplicity is quite important too, but of the talk, which I'm focusing on the true form. Sorry about that. So our result is a kind of an analogous of Cobel, Nemeti, Patrick, Popescu, Pampu, but for the true forms. So one analogous in some sense, right? So we fix a weighted graph, and we're going to say that there exists a divisor D. So again, it's going to be a big divisor, but there is also other conditions that it has to satisfy. It can be quite effective, but and here just to say that it exists, such that for all surface singularities and every good resolution, whose weighted dual graph is gamma. So the line bundle is based on 3. This is going to be important in the sequence, but if you do not know what it means, don't worry, I'm going to write down what we need from it. And what we need is that there is going to exist a subsheaf of the Kähler differentials such that the pullback of it is going to be just a principal ideal, and the base point 3 will mean that it's going to have support in the exceptional divisor, which is a principal ideal sheaf times the sheaf of all forms. So concretely, if A is a free point of EV, just as before, what we're saying is that there exists some omega in this subsheaf omega that we're considering here, such that the pullback of this omega localized at the point A is going to be x to some power mu that depends on the v times a unit dx dy. And where this mu v here is actually going to be defined as the order along v of the pullback of this omega. And this only depends on the divisor. It only depends on omega, so it only depends on d. Depends on d. Depends on the dv. Yes, coming from the dv. Okay, so we will have this nice little form here. And the kind of crucial remark here is that omega is contained in the Kähler differentials. So if it is contained, this mu v has to be bigger or equal than the matter. And this is what we're going to use in an important way. Okay. I had one more comment about this. No, I think this is okay. So this is what we're going to use. So let's go back to the example and let's see. So now I actually, in here, I did the full process to obtain a resolution of singularities of the polar. So I blew it up n times. So now we have a resolution of singularities of the polar, as we're going to see. So let me not even write. So in here now we can see if you compute it, you're going to see that the polars are resolved, and we needed n blowings up, which is what we were trying to bound. And if I take dz1, dz2, and pull it back through this normal form, and once again I will get. So now I'm just going to write like this. Minus x to the 2n dx dy. And if I pull back by this transformation even more, then what I'm going to obtain is x tilde kv squared plus 3n y squared minus 1 y squared minus 1 dx dy. And you can compute it directly from this normal form that is here. Okay. And now I do have that special term there that is coming from that differential, the bound that we obtained. And this guy is x to me v times a unit, sorry, dx dy. So if I try to pull it back, what I'm going to obtain is x tilde me v, a unit, and in here is going to appear d x tilde, exterior d x tilde to the power n y. So this is actually just equal to x tilde me v plus n times a unit dx tilde dy tilde. And now these two guys, we can compare them because we do know that the sheaf of differentials coming from here are contained in the sheaf of differential of all of the pullbacks of guys like this. So what do we obtain? Therefore, we obtain that this has to be smaller or equal to this one. And this only depends on the divisor d, so only depend on the topology. So we take that n has to be smaller or equal than mv divided by 2, which only depends on the graph. So we bounded the number of blowings up that we need to factor to resolve the family of polar curves and therefore to factor through the Nash blowing up. Now there's a little warning here. I need to do this as a warning. And the warning is that I'm putting things under the rug. Under the rug, considerations over double points. So actually over double points, the way that the differential forms are a little bit different, how they behave is a little bit different. It's not so simple to see that one's going to be smaller than the other. And if you read the paper, there's going to be a combinatorial part of the argument. It's exactly to treat the quantity. It's going to be an invariant that has actually 4 entries, and there's a part of it which is combinatorial. And it's exactly because of the consideration about the double points. So a little warning here. Now, in order to finish, I want to come back to the other result that we talked about, and the one that I'm talking about, which is the answer to question 1, which is more precise, right? It is if we are L and E, then the solution is unique. We are going to have a unique triplet and a unique triplet which represents a minimum good resolution of singularities, which factors through the point going up and the Nash transform. And the way that we prove it, well, there are 2 main technical tools here. One of them is we have to expect there's an R criteria for Lipschitz Normal Embedded normal surfaces coming from a work of Norman, Pedersen, and Pichon. So of course we do expect to have techniques which are special to LNE to the class of singularity we are interested in. But there's another point here, which is the Laplacian form. And this is what I want to talk a little bit. So we do use the Laplacian formula. We don't use the Legros-Teissier formula nor other considerations about the 2 forms. And I want to try to convince you that this is actually more general. We do believe that this is going to lead to, this is an interesting tool for this general question and others. And I want to tell you why. So the first thing is that as Lorenzo said in his talk, the inner rate is deeply related with the matter discrepancy that we just saw. So we actually can write it as QV equals plus 1 divided by MD minus 1. So Lorenzo had a similar talk just with the log here. So controlling, if we are able to control the inner rate, we control the matter discrepancy, and therefore we control the number of blowings up, how much we need to go to factor through Nash. So that's why also having this with the L singularity gives us enough control. And the second point is that the Laplacian formula of the inner rate can be seen, what Lorenzo presented in the first end, can be seen in some sense as a local version of this on the graph, local on the graph of Teissier formula. So it gives you a local version of it, which you can combine with a couple of with an observation, which is if LV is different from 0, then the inner rate is equal to 1. So combined with these two things and thinking of this as a way to bound the number PV in a better way, you can see that you can get much better bounds here. So I did not talk about this during the proof of today because we just wanted to get finiteness. We didn't search something which is effective in any way. But if we were trying to find something effective, so if we were trying to find some answer to the question 1, then I do feel like, and that's I think our feeling, that the Laplacian form is really a powerful tool in that direction. So with that, I finish my talk. Thanks a lot for your attention.
Thank you, André. Any questions? So there is a question by Terry in the chat.
So my question was, where does the terminology Mather discrepancy come from? I assume it was from the work that Mather did, right?
No, actually, that's a good question. But like where we learned about it is a paper of, and maybe Lorenzo can help me, Defernex and 2008. Let me search my computer. Here's the reference.
Yes, but I'm not sure. But the same issue.
Sorry, I don't remember all of the authors, but it's a paper from 2008. Defernex is in between one of the authors. That's
Divisorial parts.
Maybe you can help us. Defernex and Ishii. Thanks, Lorenzo. Thanks.
Ishii, yeah, you're right. The Fernet Ishii and I.
Thanks. That's why it's good to have Lorenzo in the audience. Always ready to answer.
Any other questions?
This appears before actually the paper by Lozer and Dennis Lozer.
Is that a remark or is it a question?
No, this is a confirmation.
Confirmation.
But this notion appears in Dennis and Lozer paper.
Okay.
Okay, let's thank André and everyone else who participated in the conference. Thank you very much.
And maybe, and let's also thank the organizers for organizing the conference and for all the work they put it on. I think that they also deserve.
Thank you. Nobody here to apply. Everybody to upload.
Okay, time for a cocktail.
Yeah. Sorry, everybody, we will have a cocktail without you.
Oh, what a shame. May I remind that people who are registered at the workshop in July should reserve their room at CIRM or declare whether they will attend remotely or in presence. Thank you very much.
I have a question. I haven't registered. Is it still possible to register? Because I did not know about this workshop until recently.
Yes. It is possible. You go to the website of the CIRM or of the Cher Morlaix, and the registration is still open.